Good afternoon or good day, everybody, and welcome to the fourth in this series of seminars run by the Chalmers Functional Programming Group. Today, I am delighted to welcome Kathleen Fisher.
Thank you very much for that introduction.
I will just hand it over to you, Kathleen. Thank you.
Okay, thank you very much. It's my pleasure to join everybody today. Thank you for dialing in or linking in. So today I'm going to talk about how we can use formal methods to eliminate exploitable bugs. So I'm sure you are all aware that network computers are really unacceptably secure, and essentially all computers are networked these days. And when we talk about computers, we don't just mean desktop and laptop computers, but computers that have all sorts of different shapes. So cell phones, of course, are computers these days, but so are many household appliances. Doorbells and televisions and refrigerators have internet connections, and many medical devices as well, things like insulin pumps. And all of these have security vulnerabilities. So for example, Jerome Radcliffe showed in 2011 that he could wirelessly hack into his insulin pump and cause it to deliver incorrect dosages of medication. So one class of computer that doesn't necessarily look like a computer is an automobile. So you may be familiar with this picture of a Jeep Cherokee in a ditch. So I'd like to invite you to experience what happened with this Jeep Cherokee. So wherever you are around the world, close your eyes and imagine instead that you are driving in St. Louis on Highway 64 in this Jeep Cherokee, and you are starting to drive up an overpass. And as you are driving, all of a sudden, the air conditioner starts to blare blast cold air at you, and you didn't do anything to turn on that air conditioner. And then as you're puzzling over why the air conditioner is going on, all of a sudden, the radio starts to blare hip hop, skilo music. You reach down to the volume and you try to change the volume, but nothing happens. Then the windshield wipers start to go off and the cleaning fluid shoots up onto the windshield. So now you can't see all that well. And just as you're going up the overpass, the transmission cuts out. And so now, although you're flooring it and the engine is revving really high, nothing's happening in terms of the speed. And you look in the rearview mirror and you see a semi coming up behind you and there's no shoulder to pull off. Okay, you can open your eyes now. So that experience actually happened to Andy Greenberg, who was a Wired magazine reporter. He got into the Jeep Cherokee and drove it on the highway at the invitation of Charlie Miller and Chris Balasek, who were two white hat hackers who had shown that they could wirelessly hack into this Jeep Cherokee and then control it remotely over a cell phone connection. So what Chris and Charlie were showing was in fact nothing new, in that other researchers, specifically Yoshi Kono from the University of Washington and Stefan Savage from the University of California at San Diego, had shown very similar things earlier. Specifically in 2010, they showed that a modern automobile, which is essentially a computer on wheels, is about 30 to 100 embedded control units connected via CAN bus, that if you could put software on any of those embedded control units on the CAN bus, you could spread to any of the other computers, and that you could, if you could rewrite the software in one of them, you could rewrite the software in all of them and take over control. The reaction to that first paper was a little bit muted though, because if you were plugged into the CAN bus, then you, like through the diagnostic port under the steering wheel, then you were physically in the car and you could take over control of the system physically as well. So what was the big difference? They showed a year later that they could achieve the same effect by wirelessly or by taking over control without physically touching the car at all. So they did that in a bunch of different ways. In the first way, they put a virus on the computer that the mechanic would use to diagnose what was going wrong in the car. The mechanic would plug the laptop into the diagnostic port that is required by law to be underneath the steering wheel in all cars sold in the United States after 1996. The virus would then spread from the laptop to the computer and allow them to rewrite any of the software in the car. They also showed that they could hack in through the Bluetooth interface that is there so that you can connect your cell phone hands-free to the car and drive more safely. To do that, you have to pair the Bluetooth device with the car, and they can brute force that pairing at a rate of 8 to 9 connections per minute. And that was a bug in the string copy in the Bluetooth module in the particular system that they were attacking. They also showed that they could break in through the infotainment system in the car. They created a digital version of a song that caused a buffer overflow that allowed them to take over control of the car. And that song played fine in another system. It just, the particular CD player in the car had this buffer overflow problem. And then they showed that they could break in through the telematics unit. So what is telematics? That's the system that monitors how the car is doing remotely and has lots of useful features. It's the thing that arranges to call for help if you get in an accident. It's also the thing that allows you to have the manufacturer unlock the car if you accidentally lock your keys in the car. And many vendors, or most vendors at this point, have these kind of telematic systems. So for example, GM has OnStar, BMW has BMW Assist, Toyota has Safety Connect. It's a really useful feature. So all of these features, all of these, the fact that modern automobiles have turned into computers on wheels, it's been done for really good reasons, right? The brakes are controlled by software because that allows you to have anti-lock braking, which is a really good security feature that has been proven to save a lot of lives. Steering is under control of software in fancy new cars so that people don't have to learn how to parallel park, that the car can do it for them. Acceleration is under software control so that you can do cruise control, and locks are under software control so that the company can unlock the car if you lock your keys in the car. So for all of these reasons, software is becoming more and more control of the cars, but that is introducing these security vulnerabilities where now hackers can not just break in and steal information or steal money, but can take over physical control of devices. Right, so then why is it that there are so many problems with security of systems? And the answer is basically that it's really, really hard to build a system that's secure because you have to get essentially everything right to be able to get a system to be secure. That means you have to have a good design, you have to have, communicate that design well to all the people who are involved, you have to implement it correctly, you have to make sure that there are no side channel attacks, you have to configure it properly, you have to make sure that your users are using it properly, that they aren't accidentally giving away passwords, that they have strong passwords, that there aren't malicious people involved, that the physical platform is correct, and the list goes on. So I'm just going to talk about one of these aspects, specifically the implementation errors, and what can we do to build systems that have fewer implementation errors. So although that's only one aspect of all the things that are necessary for security, I'd argue that it's a very important one because it's actually you can convert bugs into exploits that allow people to take over remote control or exfiltrate information. So for example, this chart is reporting in 2018, the first half of 2018, it's reporting on vulnerabilities. So it specifically reports on 10,599 vulnerabilities. And of those, 41% had either a publicly available exploit or sufficient information available publicly that an attacker could convert the bug into an exploit. So a bug is just a flaw in software. An exploit is something that takes advantage of that bug to allow an attacker to achieve a desired effect. So exfiltrating information or taking control of the system. So this is showing that a lot of bugs, in fact, can be converted into vulnerabilities. And what can you do with a vulnerability? So the two main things are you can exfiltrate information or you can take over control. So examples of this in 2015, Microsoft, for example, published a vulnerability that allowed remote code execution on every single Windows platform that was available at the time that was caused by a bug, a buffer underflow on the Adobe Type Manager library. So that allowed remote code execution on every Windows platform. In contrast, Heartbleed is an example of another kind of vulnerability where, again, there was a bug, a missing bounds check in the OpenSSL library that allows the theft of information in a way that there's no log, there's no record that this exfiltration happened. So these are obviously both things that we don't want to have attackers be able to do. It turns out that converting a bug into an exploit, creating an exploit, is really quite challenging. It's not something that your average programmer would be able to do. But there are hackers who are extremely clever, who are also entrepreneurial. And so one of the things that such hackers have done is show how to convert, or not shown how, but they have taken vulnerabilities that they found and figured out how to exploit and packaged them up into exploit kits that other people can just go on the dark web and buy. So this means that anybody who knows how to go on the dark web and make these purchases can now launch these attacks. So this greatly expands the set of people who have the technical capability to be able to launch attacks. Right. So that's all really bad news. We would really like to create a world where it was a lot harder to take advantage of those kinds of exploits. So the hypothesis that underlies this work is that formal methods can eliminate many of these exploitable vulnerabilities. So if you've been paying attention at all to formal methods world, your reaction is probably something along the lines of like, yeah, I've been there, I've tried that, wasn't impressed, didn't work. Right? The formal methods community has been working for something like 50 years to produce software that comes along with provable correctness proofs and that therefore doesn't have vulnerabilities and bugs. And for most of that 50 years, they've been pretty much utterly failing at proving things correct at a sufficient scale to be able to be useful for anything relevant. But I would argue that now is a really good time to revisit that hypothesis. And that's for really 4 different reasons. So what's the first of those reasons? The first is really just Moore's law, right? The architects have been doing an amazing job in increasing the amount of memory and increasing the number of cycles that we have available. It turns out that a lot of formal methods is really just very advanced search algorithms. And search, the bigger the space you can search, the better you can do. And so just by having faster hardware, we're able to do much better with formal methods than we were 50 years ago when computers were, less powerful than a tiny, tiny, tiny part of your cell phone at the moment. So that's the first one. The second one is increasing levels of automation. So this graph shows the results of SAT solving. So SAT solving is the ability to automatically come up with truth assignments for a Boolean formula, where you figure out which variables need to be true and false to make the overall formula come out to be true. It turns out many questions of formal methods can be converted into very large SAT solvers, where a formula, say, or a variable might correspond to a single Boolean variable. Of course, SAT solving is an NP-complete problem, but what researchers have discovered is that although it's NP-complete, heuristics can do an extremely good job on many problem instances. And so so every year there's a competition where people from all over the world enter their SAT solvers and compete for the right to be the fastest. What Daniel Lebert did in 2011 was he took the winners of the SAT solving competition from 2002 to 2010. He ported all of their solutions to a 2011 era machine, and then he ran all of them on the 2009 problem competition. So what's here, the horizontal axis is the number of problems solved. Each solver has 20 minutes to solve as many problems as possible. So the more you solve, the better you do. The vertical axis is what the elapsed time is. So each point represents a solver solving a particular problem number at a particular time. So the further to the right and the further lower down you are, the better you are, because the more problems you've solved in a lower amount of time. So if we just pick the 80 problem point, you can see that the best solution time dropped from 1,000 seconds in 2002 to 40 seconds in 2010. So basically 2 orders of magnitude. And that's on top of the orders of magnitude of performance improvement that came about because of the hardware solutions that we've already talked about, or the hardware improvements we've already talked about. So more automation is the second key to why now is a good time to explore formal methods. The third one is more infrastructure. So for most of that 50 years, the researchers who are working to build formal methods based approaches to solve problems were simultaneously working on the formal methods tools and working on applying them to problems. And that turns out to be just too much. Now we have a whole bunch of tools that have been already developed that are available with licenses that are usable. There's tutorials, there's textbooks, and there's support, so that maybe it's not single click, very, very easy to use, but it's something that people who are not the original developers are able to successfully use these tools. And that means now you can have people who work on the formal methods tools, and separately you can have people who work on applying the formal methods tools to solving problems. And that allows it to scale to more people and more problems. And then the third thing I would argue is a shift in the mindset of how complicated the systems are, and a growing realization that people by themselves are not smart enough, clever enough, able to contain enough complexity to be able to solve these kinds of problems without more computer assistance. So I would say a similar thing happened with garbage collection. I remember in 1996 when Java came out. Before Java came out, the general reaction was real programmers don't use garbage collection. Real programmers don't need garbage collection. That's a waste of effort and doesn't do a good enough job. And then Java came out, and then it was like, oh my God, thank God we have garbage collection. We couldn't manage to keep track of the complexity anymore. So I think that there's a similar realization coming about with higher level tools. And example is Amazon Web Services, where they have this distributed system. 1 in a million events happen every second at Amazon Web Services, and people are really terrible at coming up with intuitions for what happens a 1 in a million time. Like, as far as people are concerned, a 1 in a million event never happens. But at Amazon Web Services, 1 in a million events happens every second. And so formal methods-based tools that help drive the thought processes into weird corner cases is very helpful for finding bugs and eliminating problems before they happen. Right, so that's the 4 hypotheses. So let me just stop there and take a question if there are any questions. No questions yet? Okay, well, feel free to ask questions in Slido. I will pause again in a little bit and take your questions. So that was the starting point for the DARPA HACMS program. So the idea was, let's see if we can use formal methods to produce vehicles that are much more secure. So the basic setup is that the threat model was that attackers can't have physical access to the platforms, but that they have full knowledge of the system and the source code. So why is that an interesting threat model? So having to, like, if you can successfully attack remotely, that means that you can attack people very far away and all over the world and at large scale. So it's a bigger kind of threat. Whereas having physical access, you can only attack things that you can physically touch, which is a much smaller set of things. We assumed, and also we assumed that the system that the attackers had full knowledge of the system. So they knew as much as possible about the system that they were going to attack. We assumed that hardware was out of scope. That is, we assumed that the hardware was assumed to be correct. Now, obviously, hardware is just as subject to vulnerabilities as software. So we know that's not a good assumption, but the idea was to you can't solve everything at once. So the way that the HACMS program worked was we created pairs of platforms. So for example, we had the Arducopter, which is an open source quadcopter that all of the software is available to all of the program participants. But it's a simple little system that is perhaps not fully representative of a real system. And then we have the Boeing Unmanned Little Bird, which is a full-blown helicopter that is large enough to have 2 test pilots, but can also fly fully autonomously. Boeing's Unmanned Little Bird is ITAR restricted and proprietary, so only the Boeing engineers can actually access the system and really change the code and understand what's going on. So the formal methods researchers had full access to the quadcopter, but only limited access to Boeing's Unmanned Little Bird. To make changes in the Boeing platform, they needed to train the Boeing engineers in the formal methods techniques and then have the Boeing engineers be able to actually go ahead and make the changes on the Boeing engineer. Now, to assess, like, maybe these systems were already secure before we started. So to make a claim about the formal methods, we needed to have a baseline assessment about the security. And so to do that, we hired a world-class red team to attack the systems to start out. So they were given, again, full access to the system. They had all the documentation about the system, and they had 6 weeks to break in and take over control of the helicopter. But again, they had to do it wirelessly. They weren't allowed to physically touch the system. So they were able to do that quite easily, which wasn't at all a surprise for the quadcopter, since the threat model that the quadcopter manufacturers probably were most worried about was a threat where the quadcopter was being flown in the park, for example, and no one was able to connect to it. Not too many people were able to connect to it. But the Boeing engineers were quite surprised that the red team was able to break into and take over control of the quadcopter. So to give you a little bit of a feel for how that hacking worked, there's a video here that shows not the red team, but in fact the blue team. So some of the formal methods researchers exploring the tools that were available to help attackers break in to the quadcopter. So this video is going to show what they did to break into the quadcopter.
This is an AR drone quadcopter. We'll be using its airframe in our research vehicle in the HACMS project. Eventually, we'll upgrade its control electronics so that we can host the provably secure software that we're developing on the project. But for now, it serves as a convenient platform to demonstrate the kind of security vulnerabilities we're concerned about in HACMS. Even though it is essentially a toy, it illustrates the same sort of vulnerabilities that can be found in many network-enabled cyber-physical systems, including automobiles, SCADA systems, and aircraft.
The AR drone is controlled using standard Wi-Fi technology. It acts as a Wi-Fi access point to which you can connect with a phone, tablet, or PC running the ground station application. AirCrack is a readily available software package for monitoring and injecting traffic onto wireless networks. We will use it to attack the AR drone from this laptop. First, we identify the physical address of the drone access point. Next, we send commands to deauthenticate all clients, including the ground station. The ground station now has no control over the vehicle. The attacker laptop has taken control of the vehicle, and the ground station is not able to reconnect. Finally, we can send arbitrary commands from the attacker laptop. In this case, we will simply cause the vehicle to land.
Even though this was a very straightforward attack, it is representative of some of the current threats to network cyber-physical systems that we will address in the HACMS project.
Right. So the video shows that it was actually quite easy to break into the quadcopter. It was a little bit more difficult to break into the unmanned little bird, but still doable. So then the researchers, the blue team researchers, got to work, and they were able to replace the software and some of the hardware on the quadcopter. So this graph shows a wire diagram of the changes that they made. So the time kind of goes towards the right. It started at time 0. They started with the monolithic software stack that came with the quadcopter. There's no real-time operating system and no security. So then in the first 6 months, they re-architected the system. They replaced the underlying hardware so that it ran now a PX4 ARM Cortex M4, which had slightly more processing power. They then put a free RTOS on top of the hardware, and then they added a hardware abstraction layer, and then the rest of the software they refactored to run on top so that the software didn't know if it was running on this more powerful processor or the original processor. Then they got to work creating higher assurance versions. So NICTA, which is now Data 61, started working on replacing the free RTOS with eChronos, which is a verified real-time operating system. Galois got to work in designing a couple of domain-specific languages embedded in Haskell. The Ivory domain-specific language is a sub-Turing complete language that allowed them to generate fragments of C along with proof obligations that would allow them to prove that the C code running on the quadcopter was memory safe, for example. And then a Tower real operating system that allowed them to identify tasks that operated concurrently and be able to communicate with each other. And then Rockwell Collins built a proof environment that would allow them to take the facts and proofs about various subpieces of the system and put it together to build an overall proof of correctness of the overall system that they could then, if you swapped out a piece, it would tell you that you needed to redo part of the proof. So by the end of the first 16 months of the program, when they had to turn over the new and improved, now they call it the SMACM copter, to the red team for assessment, we had a fair bit of the piece in a code verified to a higher level of security. The also from the high level, the work that Rockwell Collins did also generated a high level architecture description, and from that generated the glue code that connected everything together. So the parts that are green in the diagram were notionally built to a higher assurance standard than the parts that were white were still residual. So what had they accomplished by the end of the 16 months? So the SMACM copter at that point was able to fly. It had stability control, altitude hold, directional hold, and a new feature, specifically denial of service attack detection. It had GPS waypoint navigation that was about 80% implemented. So the original one had full GPS waypoint navigation. So that was the one place where the functionality of the modified SMACM copter didn't quite match the functionality of the original copter. And our team used the formal methods-based tools that they had developed and applied to prove a bunch of system-wide properties. So they proved, for example, that the system was memory safe. They proved that the system ignored all malformed messages. They proved that it ignored all messages that weren't authenticated. And they proved that all good messages received by the SMACM copter would actually eventually reach the motor control. Now, this is, of course, not fully this is not full functional correctness. This is actually a fairly low level of correctness. But when they turned the system over to the red team, The red team had participated in all the design discussions. They knew all about the architecture. They'd seen all the code. They had 6 weeks with the resulting system. They were able to find no security flaws in that 6 weeks. So even though the level of assurance was relatively low, it was enough to keep the red team out of the quadcopter. My colleague at DARPA at the time, who was an expert in penetration testing, his assessment was that that quadcopter was the most secure UAV on the planet. And my boss at DARPA, the head of I2O at the time, he came and told me afterwards that that result by itself fully justified the entire expense of the HACMS program. That when they funded it, which they funded it to roughly $70 to $80 million, they thought it was going to fail, that it had no chance of success. But just the quadcopter and that penetration testing exercise was enough to demonstrate, at least to DARPA's satisfaction, that formal methods were really worth exploring in more detail. And all the software that was developed for the SMACM copter has been made available open source. So that was just after the first 16 months of the program. The first 18 months, the program had 2 more phases and 3 more years to go. So the researchers didn't stop there. They started to apply the same tools and techniques to the unmanned little bird instead of to the quadcopter. So they took the quadcopter and they re-architected it so that its architecture more closely matched the unmanned little bird. Specifically, it had 2 computers, one of which is the flight control computer that controls things like stability and altitude hold, the kinds of things that the SMACM copter was doing in phase 1. And then a second computer is the mission control computer that talks to the ground control station and then tells the mission control computer what to do. That flight control computer directs the helicopter about where it's supposed to go, and also controls a camera to figure out, take pictures, fly here, take more pictures, things like that. And so during phase 2, the red team, or the blue team, put SCL4 microkernel on the mission control computer and created different partitions. So one of the partitions was to talk to the ground control station and to talk to the flight control computer. That partition, all of the code that was put into that partition was written using formal methods-based techniques. It was verified to be memory safe and, to the extent possible, to be functionally correct. That code was controlled very, very tightly. In contrast, there was a second partition that was set up. That was for the camera, and that was where they put legacy code that they didn't have time to verify or weren't interested in verifying. And there, they basically assumed that the code in that partition was written by bad guys. And so the challenge in phase 2 became, and phase 3 was, if the bad guys were able to put code in that partition, in the unsecure partition, would they be able to disrupt the operation of the helicopter? So at the end of phase 2, instead of forcing the red team to attack remotely, the red team was allowed to put whatever code they wanted on the mission control computer in the partition for the camera. And they were challenged with breaking out of that partition and disrupting the operation of the helicopter. And they turned out they were not able to do that. Again, even though they had access to all the design documents, they understood how everything had been put together. So they were not able to disrupt the operation of the quadcopter, of the helicopter. So at the end of phase 3, they repeated that experiment, but this time while the unmanned little bird was in flight with 2 test pilots on board. Thankfully, the same result happened, which was that the attackers were not able to disrupt the operation of the helicopter. These results led to the inclusion of language in the John McCain National Defense Authorization Act, which is the thing that the US government uses to authorize military spending, that directed the Pentagon to explore using, it specifically mentioned, HACMS-like technology to develop systems that would be much harder to hack into in the future. Also during phase 3, because of the successes in phase 1 and phase 2, HACMS researchers started working with various other platforms. So other kinds of quadcopters, truck convoys, satellites, underwater vehicles, all of which the idea of applying these kinds of techniques to produce much more secure systems. I will pause there for questions. Mary, are there questions now? All right. Okay, so let's see. Any thoughts on using formal methods to test hardware design? So I think that, in fact, yes, hardware is also something that is amenable to formal methods-based design. In fact, hardware in some sense was amenable, and people started applying formal methods-based techniques to hardware-based approaches even earlier than software-based approaches, partly because the testing problems for hardware became more obviously infeasible earlier than on the software side, and also because of the Pentium bug causing $500 million, a lot of damage to Intel. So yes, absolutely, formal methods-based approaches are also applicable to hardware. And there's a question is, were the missing 20% of implementation of the copter due to lack of time, or were there something particularly complicated? It was really just due to lack of time. They ran out of time. Then how big was the red team compared to the blue team? So the red team had something like 10 people-ish order of magnitude, and the blue team had something like 25. So the blue team was definitely larger than the red team. The blue team did participate in all of the design meetings of the red team, so that they were, in some sense, part of the blue team as well. Then would the usual workflow consist of first formalizing and method proving followed by implementation, or does it double up for formal proof and implementation? Yeah, so let me talk about that one as I go on, because that point comes up in the next part of the talk. And then the next question is, although you haven't explicitly made the connection, you imply that upgrading the CPU power has an impact on exploitation. Why do you think that is? So the issue there was upgrading the CPU made it so that the defensive software was able to execute more powerful code. So I think we're reaching a tipping point where any processor that's available is going to be powerful enough to be able to do the necessary things for security, but cryptography is a key bottleneck. So if you can't do cryptography, then you can't do authentication, you can't do integrity checking. So the ability to use cryptography is super important. So if your device is sufficiently power weak that you can't do cryptography, then you're not in a very good situation. And the canonical example of that has been medical devices that are embedded in the body. So pacemakers, for example, there's a very limited capacity for battery, or at least in the past, and it wasn't sufficient to do encryption. But battery technology is getting better, and we're able to do encryption with less expensive methodology. So that's a place where the CPU power is really important. Okay, so maybe I will go on, but I will take more questions in a little while. Okay, so that's some evidence. DARPA HACMS program basically provided some evidence at scale that convinced people in the Pentagon, at least, that formal methods were worth exploring. So what exactly are formal methods? I've been talking about them for now, half an hour without actually defining them at all. So when I started putting together this talk, I looked around to find out, formal definitions of formal methods. And this is the one that appealed to me the most, which is formal methods are best described as the application of a fairly broad variety of theoretical computer science fundamentals to problems in software and hardware specification and verification. So like completely super vague, doesn't really say very much. It's a little bit like Justice Stewart's famous comment about, I know it when I see it. What I would say is formal methods-based techniques are based on math. They are in some way machine checkable. They're capable of proving properties about both code and models, usually models. It's super important to read the fine print. All formal methods-based approaches make assumptions about the system, and those assumptions might be unreasonable. And then they promise guarantees, and those guarantees may be too weak. So basically, it's really important to read that fine print. There's a whole range of different formal methods-based tools. So this notional graph illustrates the range of different kinds of tools I'm talking about. So here, the horizontal axis represents the level of user effort and how scalable the system is. So on the left-hand side, tools are fully automatic and can scale basically to as much software as we know how to write. So an example at that part of the spectrum is type systems, right? Type systems are formal methods-based tools. They allow us to prove properties about our programs, and they can scale to as many lines of Haskell or Java as we care to write. Whereas at the far right-hand side, it takes PhD years to be able to prove properties, and we can prove properties about thousands of lines of code. I would say the state of the art nowadays is somewhere around between, less than 100,000 lines of code. But that's getting bigger. Then the vertical axis is how strong a guarantee do you get? At the very bottom, we have things like type safety. That's a property of a program, but it's a pretty weak property of a program. Whereas at the top, we have full functional correctness. And there are different formal methods-based techniques at each of these points in the spectrum. So as I mentioned, at the bottom left are type systems. At the top right are interactive theorem provers. And in the middle are things like symbolic execution, model checkers, sound static analyzers, verified runtime monitors, and then automatic theorem provers. And the orange type here are examples of systems that have been proven to have desirable properties using each of these different kinds of approaches. So we can see that there are useful things that you can do at any one of these levels of effort. Right. So, of course, like I mentioned, the number of lines of code we're talking about here is 100,000 lines of code, something in that order. And if you look at Windows or Linux, we're talking about like 100 million lines of code. So we're nowhere near being able to verify all software. And I would argue that we will never verify all software. It's not an interesting question. It's not the right question. It's not a useful level of investment for most software. What I would argue is, are there key pieces of software, exquisite artifacts, that if we could verify those artifacts, could we then use them to build more complex systems that we have, for which we have much more security guarantees that are much, much harder to hack into? And I would say that HACMS is an example showing that, in fact, the answer to that question is yes. By leveraging the SCL4 microkernel, we were able to verify, to build a helicopter that was much more secure, even though we didn't verify all of the software in that system. So if you start to think about, like, what are the exquisite artifacts that if you could just have verified high performing versions of those systems, we could leverage those to build much more secure systems, the things that come to mind are things like separation kernels, hypervisors, real-time operating systems, compilers, garbage collectors, file systems, web browsers, sandboxes, and cryptography primitives. And the really great news is that in all of those categories, there are already systems that have been verified to be fully functionally correct. They may not be as fully featured as the state of the art, but they are featured enough to be able to do a lot of good work. So I just want to highlight two specific examples. So the first is the SCL4 microkernel. So what is a microkernel? Basically, the microkernel is the core essence of a microkernel of an operating system. It's the part of the operating system that absolutely positively has to run in privileged mode. So the group at NICTA Data 61 implemented and proved correct a microkernel in Isabelle HAL. That code was 10,000 lines of C code and 480,000 lines of proof in Isabelle HAL. So quite the overhead in terms of the proof. It took them 13 years to build the operating system and prove it be correct. So 2 years of design and 11 years of implementing, person years. And then the 8 person years to update the infrastructure and the theorem proving support. So if they had to do it again, the 8 would be in the infrastructure and the 13 would be redoing the operating system piece. So 13 was for operating system pieces, 8 was for formal methods tools. The resulting microkernel has the fastest known one-way interprocedural code fast path. So that's the key metric for the speed of a microkernel. So there was no performance hit for using a verified version instead of using a non-verified version. And the set of properties that they've proven about the microkernel are quite impressive. They ranging for up to, including full functional correctness. So for example, they proved access control enforcement. That means that, so part of what it's doing is providing separation. So they proved that only the users that had authentication were able to access the corresponding resources. They proved that if you had 2 different partitions, that those 2 partitions couldn't interfere with each other. They proved that the compilation of the C code that they wrote the microkernel in down to binary, that the binary had the same semantics as the C code. And then they proved that the IPC fast path was correct. And all the code is available open source. So the graph here is the call graph of the SCL4 microkernel. And I think looking at that suggests one of the reasons why the proof is so complex, in that doesn't look very modular, right? Like, sort of by design, the microkernel is everything touches everything else. And so it's very hard to break it apart. And the properties that you need to prove are kind of system-wide properties. Okay, so that's one example. Another example is the CompCert Verifying C Compiler. So this is the subset of C that's used by the aviation industry. So the key parts of the language that are omitted are concurrency and separate compilation, although both of these are projects that have been worked on quite a bit since Xavier published the original paper in POPL in 2006. Xavier Leroy implemented the CompCert Verifying C Compiler in Coq and proved it correct, and then extracted the actual compiler. The overall development was 42,000 lines of code plus proof, so significantly smaller than the proof effort required for CompCert. I think, hypothesis as to why that is, if you look at the diagram there, that's the architecture of CompCert, where there's a whole bunch of phases. And the proof basically shows that the before and after of each of those phases preserves semantics, sometimes by actually proving that whatever is generated is correct, and other times by generating something and then proving that the generated thing has the same implementation as the previous stage. So it's much more modular architecture. It took 3 person years to build the compiler and the proof. Of course, those are Xavier Leroy years, which maybe doesn't translate into mere mortal years, but still 3 years. The speed of the resulting compiler, it's twice as fast as GCC at 0 level of optimization, 7% slower at 01 and 12% slower at 02. So quite an impressive feat. Right. Okay, so maybe I can take another couple of questions. So then the first question is, how effective was the McCain bill at encouraging subsequent use of formal methods? The answer to that is I don't fully know. DARPA has continued to invest. There have been subsequent follow-on programs in using formal methods, and there have been continued partnerships with various parts of the military. So my guess is that they are doing quite a bit in this space, but I don't actually know. Then, is design by contract formal methods idea to add pre and post conditions check to function? Where would it lie on the formal method effort scalability chart? So yes, I would say that design by contract is a formal method. It would lie above type systems and below full functional correctness. Some of it would depend on how detailed the specifications were. If the specifications were type system-like, then it would be closer to the type system side, whereas if they were closer to full functional correctness, it would be closer to the higher end of the spectrum. Yep. So then, let's see. I would give a similar answer to the question about Hoare type theory. So somewhere in the middle. The questions are disappearing. So then the question is, how easy will it be to use formal methods instead of test cases in backend systems? So I think test cases and formal methods are complementary. Formal methods can prove that an implementation satisfies a specification, but how do you know that the specification is correct? You can't use formal methods to verify the specification. You can do some sanity checking, but you can't verify the correctness of the specification per se. Instead, you need to validate the specification, which is usually a testing-based regime. So to produce systems that are secure, well, maximally secure, to our best of ability, you need to do a combination of verification and testing. And that by having really rich specifications, that can help guide the testing regime, both to test the specification and to figure out where more interesting test cases should come from. Okay, let me go on to the next section of the talk. Okay, so I've talked about, sorry to move the slides around twice on you. So I've talked so far about the HACMS test case of showing formal methods can be used in real systems, and I've talked about what formal methods are. Like, why isn't everybody using formal methods already? So obviously there are a bunch of good reasons for that. So one of them is the problem of expertise. So this chart shows the result of a survey. It was published in 2009. I think the actual survey was done in 2006, calculating how many researchers in formal methods were there around the world. And the answer was less than 5,000. So like tiny, tiny, tiny drop in the bucket compared to the number of developers, say. I think this situation is getting better. Since 2006, there have been a number of courses at different universities. There are a lot more resources available. So, maybe now there are 50,000 researchers. So a lot more, but still nothing compared to the number of researchers, the number of people who are writing software. So we need to have more people who can use formal methods to be able to get them used at scale. Another issue is the required level of effort. So we saw with the SCO4 example that the overhead for the proof was really quite high. This chart shows a number of the artifacts that I mentioned earlier, the exquisite artifacts that would be useful for building more high assurance systems, compared like how long, it shows what they are, how many lines of code they are, and then how much time it took. And you can see that the SCO4 project is really quite an outlier, that most of the systems are substantially less. And if you think about I think a key question here is, what's the return on investment? So how much does it cost to develop the system to the higher level of assurance versus how much can it save? One of the challenges in writing secure code in the past has been that the people who are responsible for developing the code are not typically the people who are responsible for paying for the effects of bad code. So if there's a bug that allows an attacker to break in and take over control, it's not the software developer's responsibility to pay for that, to pay for the damage. And we've seen in the last decade pretty monumental damage.
Yes, start from there.
Okay. So another possible impediment to the adoption of formal methods-based approaches is the performance of the verified system. The slide lists a number of formally verified systems and the associated performance. And you can see from the data on the slide that it's often, but not always the case, that the verified version is slower. I would argue that the verified code is not intrinsically slower, but the way in which fast code is often produced is you write a system and then you measure its performance and you realize there's a key bottleneck, and then you add a fast path that copes with that particular case, and you keep doing that until you get fast enough performance. Of course, every one of those special cases that produce performance adds another burden for the verification. It's another thing that has to be proven. And so when people are doing verification efforts, they basically only verify as many fast paths as necessary to get good enough performance, and then they stop. So if you look at the data here again, what I would say is that we're getting fast enough performance to be used in practice. So for example, Amazon has started using a verified version of TLS in their web services, and they wouldn't be doing that if it wasn't fast enough to be used in practice. Another possible impediment is the delay that is introduced by having to do verification in addition to writing the code. If you have to write the code and verify, it's going to take longer than if you just have to write the code. So one of the things that's really promising in this front is the work that, say, Facebook is doing with the Infer tool that is integrated very closely into the development lifecycle, so that when a developer checks in a change to the Facebook code base, the Infer tools run and report back bugs that the developers are required to fix before they can finish the check-in process. And that means that the bug is still very much top of mind. It's still, it's part of the normal code review process to have this kind of review information coming back, and the programmer can't sort of check it off as done until all of these mistakes have been dealt with. So that's a fantastic innovation. The limitation is that it's kind of towards the bottom end of the formal methods tools, and that it's only proving relatively simple properties like the absence of null pointer errors and resource leaks, but still a very promising direction. Similarly, there's work at Amazon Web Services where they wanted to verify the TLS, the transport layer security of their services. And previously, Andrew Appel and his team published in Usenix Security a proof of the high-level specification down to a relatively high-level implementation. What Amazon Web Services have done with Gao's help is taken that high-level specification, or that high-level implementation, and mapped it down into very performant C code in a way that they can connect the proof that Andrew's group did all the way down to the bits, and do it in an automated fashion, so that when developers change the proof of change the implementation, the proof can be automatically redone and connect back the new bits all the way up to the high-level specification. So in the paper that they published about this, over a 12-month period, they changed the implementation 956 times. And of those 956 times, only 3 times did a proof engineer have to come back to be able to redo part of the proof. The other 953 times, the proof was able to be updated entirely automatically. So these are both evidence of ways in which you can connect a formal methods pipeline into the normal development process in a way that the proofs are automatically updated and maintained as part of the development process. So then we get to the fine print. Remember, I talked a while ago about how formal methods make assumptions and they may not guarantee what you actually care about. So an example of exploring the fine print is the work that John Rieger and his group have done with CSmith in exploring bugs in compilers. So he found 325 bugs in various C compilers, including CompCert, even though CompCert had been verified. The bugs in CompCert were in the unverified front end, i.e. the parser, and in a hardware model. So the bug and the front end has been fixed, and the front end, the parser, has subsequently been verified. The hardware model, that goes to what I talked about earlier with verification and validation. The model is an assumption about the hardware, and you have to test that your model accurately reflects reality. If it doesn't accurately reflect reality, then your proof doesn't apply. So even though that there were bugs, John Rieger's group was quite impressed with the quality of CompCert, right? They didn't find any more bugs, and it wasn't for lack of trying. They had essentially tested, they spent about 6 CPU years trying to find bugs, and those were the only bugs they were able to find in the C compiler. Okay, so taking stock, where are we? So we've been talking, or I've been talking about how formal methods can be used to fix them, to find and identify implementation bugs and make implementations that are much higher quality and therefore much less likely to be able to be hacked. Formal methods are not just good for fixing implementation bugs. There are other parts of that stack of things that the security-minded developer has to worry about. The reason why there's a picture of an octopus here is that there's so many things you have to worry about. Even an octopus doesn't have enough arms to take care of everything. But formal methods can help the octopus with more than just correctness. It can help with design. So for example, the way Amazon Web Services is using model checking, they're not actually model checking the implementation, they're model checking a design to find design errors, not implementation errors. Rockwell Collins was able to use their tools to find mistakes in the specifications. NICTA used formal methods-based approaches to find side channel leaks, and then all of these can also be applied to third-party software. So there's more things that we can do with formal methods than just work on implementation errors. There are a lot of lessons that have been learned. So one of the key lessons is to not try to verify existing code, but rather to co-develop the code and the proof. There's a couple of reasons for that. One of which is, as you're developing the code, there are lots of choices where you could do it one way or another way. Maybe one of those ways has consequences for correctness and the other one doesn't. And this allows you to choose the one that will make it easier for verification downstream. Right. And then there are, of course, many, many, many remaining challenges. So one of those example is getting buy-in and training. So when the group at Amazon Web Services started to introduce model checking, they didn't talk about model checking. What they did was, like, one guy basically read a paper about model checking and decided that it was really important that they start to use those kinds of techniques because he was worried about the 1 in a million effect. And so he did a prototype with using TLS and was able to find a bunch of mistakes. And so he got a buddy involved, and the two of them were able to find a bunch of mistakes. So when they went to explain to the rest of their group and to try to get the rest of the group to use them, they didn't talk about formal methods and they didn't talk about model checking. They talked about exhaustively testable pseudocode, which people didn't already have negative mindsets about. So figuring out how to reach your audience is a very important piece. And then the sort of double elephants in the room are handling concurrency, right? Concurrency blows up the state space, and so it makes it much harder to deal with. So this is an active area of research, is figuring out how to apply formal methods-based techniques in concurrency settings. And of course, all the things that I've been talking about in software apply to hardware as well. But despite all that, I think that we're actually within reach a vision where critical parts of critical software are actually built out of verified components and their composition is verified so that buggy software is no longer an easy attack vector. I think we're actually getting reasonably close to this point already. I think that's part of the reason why we're seeing so many more hardware attacks, is that the low-hanging fruit maybe is on the hardware side now instead of the software side. The advantage of getting to this is we're not going to make it so security vulnerabilities don't exist, right? Security is always going to be a problem, but it does make it so that the security vulnerabilities don't scale as well, right? If Black Hat has to physically go and touch your car to be able to hack your car, then the number of cars he can attack in a given day is much, much, much lower. Annoying, but not a national security threat. At this point, I will stop and take any more questions. And this, yeah, thanks go to lots of people that are listed on this slide. Okay, questions. Are there any significant examples where the unverified version did all kinds of dynamic checks that formal methods allowed to skip, giving better performance? So I've heard anecdotes about things like that. Adam Chapala talks about a garbage collector where the garbage collector at runtime was able to not do a certain check because they could prove formally that that case didn't actually need to happen. I haven't seen it a lot. So I think in practice, it probably doesn't happen all that often, but I mean, a different answer to that question is type systems, right? So if you have a static type system, then you can remove all sorts of dynamic checks because the static type system guarantees a whole bunch of properties. So at the low end of the spectrum, we see this all the time with statically type checked languages having better performance than dynamically checked languages. So yes. Then the next question, how can we be sure that a certain set of properties together forms correctness? That's a really hard property. That's a really hard problem. So that is related to my point earlier about verification and validation. So most of the talk, I've been talking about verification, which is proving that a implementation matches a specification, but proving that the specification is what you want is a very, is challenging in its own right. And that's something where testing is really important, and simulation, being able to develop experience with the system and making sure that the properties that are implied by the specification are the ones that you actually want. So it's by no means, like, verification is not at all a silver bullet as far as the validation and whether the correctness that you proved is the one that you actually care about. Okay, next question. Since it's Chalmers FP, can you connect FM with the topic of language tech? Are existing languages good enough for applying formal methods? Need better languages? Functional, right? So yes, there's obviously lots of connections between formal methods and functional programming. So functional makes it much, much easier to verify. You don't have to worry about all sorts of side channels that can come about through state. So, very carefully controlling where state is a really important technique. I think one of the really interesting things is that the systems that have the highest level of assurance in terms of formal methods proofs are typically written in C, where of course we know that C is not it's a terrible language as far as security is concerned. I think one of the interesting reasons for that is if you wanted to verify Haskell, for example, you would need to verify Haskell's runtime system, which is an enormous C program. So you need to be able to verify C code to bootstrap proofs of correctness of higher level systems. I think that it would be fantastic if we didn't ever need to write C code, because C is a terrible security vulnerability. So higher level, or languages that deliver very good performance that is precisely under control of the user, that allow low level systems programming in a type safe way or a formally verified way, things like Rust, or feature variants of Rust that allow higher level security properties to be integrated, I think is really valuable and really important, and something that will likely happen over time. Okay, next question. Do you verify C source code, say, or the resulting binary with all the optimizations in a way of verifying the compiler on top of the program? Yeah, so that's a really good question. Mostly we were verifying the C code, and we were not trying to map down to the binary. There's an obvious possibility of connecting the CompCert Verifying C Compiler to connect from the binary, from the C code down to the binary. We didn't do that. We ran out of time. The CompCert Verifying C Compiler did in fact map from the C code down to the binary. They did that by, there's a PLDI paper about how they did that. It's super clever. They used model checking to prove that the generated code matches the semantics. They didn't verify the compiler, and they didn't use CompCert. The reason they did try to use CompCert, the challenge was that an idiom that was very popular in the SEL4 triggered a really bad performance part of CompCert, so they couldn't afford the performance that was produced by the CompCert Verifying C Compiler. Also, they had slightly different models of the C code that were involved, so there's still a lot of work to be done in connecting all the pipelines together. But I think at this point, we understand. I would say collectively we know how to do it. We just don't yet have the engineering resources and will to actually do that piece. Okay, next question. Wasn't SEL4 verified to begin with a Haskell prototype, and CompCert is in Coq? Yes, indeed, that's part of the problem for connecting CompCert. So yes, SEL4 was verified. The original design was done in the context of Haskell, and so the SEL4 group had a group of experts in formal methods and a group of experts in operating systems, and those two groups figured out how to develop a shared vocabulary around Haskell. So they wrote a prototype implementation in Haskell and used that to have these two groups talk to each other. And then the formal methods engineers went about proving the properties, and the operating systems people went about implementing it as C code. And they connect a kind of nice commuting diagram that proves that the C code correctly implements the Haskell specification, which correctly implements the higher level specifications. And then the C code, when mapped down into machine code, that there's a semantic property that's maintained there as well. Yes, and the whole SEL4 development is in Isabelle, and CompCert is in Coq, which is part of the problem why it's not easy to connect those two together, because they have incompatible logics. Okay, next question. This technology seems well suited for the crypto financial ecosystem. How quickly can new competent formal verifiers be trained, and how much do they cost? I presume formal verifiers are people and not machine learning systems. So let's see. I would say it takes about a year to get some, well, my experience working with PhD students is it takes about a year from when people start using Coq to being able to use Coq to accomplish a purpose, as opposed to use Coq to learn how to use Coq. And that those people are, relatively smart people who might be PhD students, say, level of people. So it's still not as easy as it should be. But with all the materials like the software foundations, et cetera, that have been developed, it's much easier than it was before. I have an undergrad who spent fall semester or spring semester working with one of my PhD students to get up to speed, and he's now working over the summer to prove properties about a lexer. So I guess I will know by the end of the summer if one semester was enough to be able to get useful proof out at the end of the summer. How can C be improved to make verification of low-level first-order programs easier? Yeah, C Rust, I think. And then how can formal methods be used to make programming more fun and joyful in addition to more useful? Well, lots of people talk about how using interactive theorem provers is like a video game. It has some of the experience of getting points for whacking theorems down. Maybe a better user interface might make that easier. Yeah, I don't know the answer to that question. When I was at DARPA, one of my colleagues, Drew Dean, created a program on the gamification of formal methods. Could you map formal methods-based problems into video games of various kinds that you could then crowdsource? Sadly, I don't think that was very successful. I don't think that they were able to design games that people actually thought were fun to play. Of course, like the motivation was like the fold it effort, where people actually do enjoy playing games that correspond to folding proteins that have been turned out to be very useful. And there are some people who are idiot savants at folding proteins, people who have all sorts of strange backgrounds who are incredibly good at folding proteins. So maybe if we did a better job of gamifying formal methods, we could find people who are really good at proving theorems without knowing that that's what they were doing. And I think that's the last
I
question.
think on that note, Kathleen, I'd like to thank you very much for your talk. Thanks to everybody who's been listening. And that's the end for today.
Thank you very much.